introduction, and thank you to three organizers for the opportunity to give a flash talk today. And so it's interesting to give a talk in this new format. Let's see how it goes. So the purpose of my talk is to illustrate the advantages of working with enhanced triangulated categories when studying derived categories of rings and algebras. And for that, I would like to give a rather simple proof of a slight generalization of a theorem of Ladkani concerning derived equivalences between upper triangular and upper triangular matrix rings. So this is the theorem I want to prove today. So the input is the following. So you're giving three rings, or more generally differential graded rings, R, S, and E. And the methods I will use today even allow to extend this result to the more general context of ring spectra in the sense of stable homotopy theory, in case you know what those are. Now, as I mentioned, I'm interested in certain upper triangular matrix rings are displayed here. So for that, I will need a DG bimodule, or a complex of SR bimodules if you want, M, which is perfect as a DG module over R. So it's a compact object of the derived category of R. And moreover, I will need a invertible DG bimodule over E and R. So it's just a DG bimodule over these two DG rings, such that the tensor product with T is an equivalence. So what Ladkani proved in the case where all the things in sight are rings and modules, or rings and bimodules, is that there is a derived equivalence between these two upper triangular matrix rings. And I want to explain a proof that also gives a result for DG rings, or for ring spectra. Okay, so the main ingredient in this proof is the so-called gluing along exact functor. So this is an operation that one can perform as soon as one is working with enhanced triangulated categories. I hope you can see this. So for concreteness, I will work in the model given by stable infinity categories in the sense of Lurie. So if you don't know what these are, just think about the refinement of the notion of triangulated category, such that the things I will say are true. And these are all things which are always false for triangulated categories in some sense. Okay, so what is the gluing along an exact functor? So giving an exact functor between enhanced triangulated categories, I can glue A and B along this functor by considering the following homotopy pullback of enhanced triangulated categories. So I take the functor F and the category of morphisms in A, which is again an enhanced triangulated category. So this is also an enhanced triangulated category. And I consider the functor that restricts a morphism in A to its source. And then I consider the following pullback. This again is an enhanced triangulated category. So you can think of the subjects of this new enhanced triangulated category as pairs, little b in B, together with a morphism phi in A, such that the source of phi is f of B. That's written here. Of course, I could have done something slightly different. I could have, instead of taking a morphism in A and restricting it to its source, I could have restricted it to its target. Yeah? So that will give me a different homotopy pullback, which I denoted L upper star of F. And the point is that all of these are enhanced triangulated categories, and all these functors are exact functors between enhanced triangulated categories. So this is something which is already very useful, that I can perform this gluing operation, which in this language is essentially equivalent to the notion of a recoulement. Now, the second main ingredient is a canonical equivalence between the two different ways to perform this gluing. So this is some kind of folkloric result. The proof I put here, it's come from a paper from 2019 together with Dickerhoff and Valde. And we call them universal BGP reflection functors because, well, they are given essentially by the same formula of the Bernstein-Gelfand-Ponomarev reflection functors, and they're universal in the sense that all BGP-style reflection functors we know about are instances of this equivalence. And here, the way we construct these functors is also in some sense quite simple, because it exploits the fact that the gluings are defined in terms of pullback diagrams. So here I have the diagram that defines L upper star of F. And here I have the diagram that defines L lower star of f. And as it turns out, these two diagrams are related by equivalences. So I can put here simply the identity functor. So obviously f commutes with the identity. And here I can mediate between restricting a morphism to its target and restricting a morphism to its source, which now I put also with a t, using the cone and the cocone functors. So that's another thing we can do with enhanced triangulated categories. Cone and cocone gives me, in fact, autoequivalences of the category of morphisms, which are inverse to each other. Now, once I take the pullback, by the universal property of pullbacks, I will get induced functors between the gluings, which are essentially given by taking cones and cocones as indicated here. And the fact that cone and cocone are inverse of each other means that S minus and S plus, these reflection functors, are also inverses of each other. Okay. So in some sense, it's an easy observation that there is this canonical equivalence. Okay. Now, third ingredient is what happens when we glue along an adjunction. So if you glue along an adjunction between enhanced triangulated categories, there is a kind of tautological equivalence between the L lower star of f, so this is the sort of covariant gluing of A and B along f, and L upper star of G, which is essentially given by passing from a morphism to its transpose. I added here a remark for those in the audience who may be familiar with adjunctions of infinity categories, and the remark essentially says that in a correct interpretation of these gluings, this statement is truly a tautology because after interpreting these two categories in a specific way, they turn out to actually be equal. So this is really a tautological equivalence. So when I glue along an adjunction, I'm allowed to flip the position of the star in this way, and at the price of changing from the left adjoint to the right adjoint. So to finish, let me explain how to use these three equivalences to prove this theorem of Ladkani now for digi rings and digi modules. So here was the input data. So there is a digi bimodule over S and R, which is perfect as a digi R module. Here there is an invertible digi bimodule over E and R. So that means that this is an equivalence. And the first thing is I consider is the following commutative diagram, which has the equivalence induced by tensoring with T here. This is just the R hom out of M. And this is just the composite. Now, the first observation is that the assumption of M being perfect as an R module means that this functor preserves coproducts. And since this is an equivalence, it also preserves coproducts, so the composite also preserves coproducts. And by a version of the theorem of Eilenberg and Watts, this means that the composite, which is here, is given by tensoring with an appropriate bimodule, which is this bimodule with the residual action of E and S here. Okay, so with that, we now can give a proof of the theorem. So the first thing is that there is a less trivial equivalence, which comes from a recognition theorem proven by Keller for derived categories of digi rings or ring spectra, proven by Keller for digi rings and Schoed and Shipley for ring spectra, from which one knows that the derived category of this upper triangular digi ring is L lower star of the functor tensoring with M. Now, this functor is left adjoint to the R hom functor. So by the adjunction equivalence, I can flip the star to the top and pass to the adjunct functor. By the BGP reflection functor, I can simply flip the position of the stars. Now, using the fact that the gluing is defined as a pullback, this square here immediately induces an equivalence between these two gluings, because these two vertical arrows are equivalences. And by a version of the first equivalence, I see that L lower star of tensoring with this bimodule is the derived category of this other upper triangular matrix ring I was interested in. So this is the proof I wanted to present. As you see, it's in some sense using three sort of very basic equivalences. And here's just a slide I want to display at the end. So I think I'm out of time. But yeah, this was extra. Just all the information that you need to know to prove this equivalence together with the recognition theorem. Yeah, thank you very much.